Hi everyone, welcome back to Power Chemistry Daily Question and Solution. So over here today, we are still on ionic equilibrium and we are looking at buffers. So before I go into the question, I'd like to give a slight introduction about buffers. There are two different types of buffers. First would be acidic buffer. For acidic buffer, it has to contain two different components. The first one will be a weak acid. For example, CH3COOH ethanoic acid, as well as a salt containing the conjugate base of the weak acid. So for example, that would be the conjugate base would be CH3COO-, and the salt will be after this anion combines with a cation Na+. So an acidic buffer has these two components. Another type will be the alkali buffer. So alkali buffer is the opposite. So it has to consist of a weak base, for example, ammonia, and a salt containing the conjugate acid of the weak base. So that would be NH4+. So over here, I'll have to check whether each of the options contains the components required for the buffer or not. So let's look at number 1. I have 10 cm³ of 0.1 mole per dm³ of ethanoic acid. So this is my weak acid. And I also have my 10 cm³ of 0.1 mole per dm³ of sodium ethanoate. So CH3COO- is within the salt. CH3COO- is the conjugate base of your ethanoic acid. Hence, over here we have the weak acid and its conjugate base. Therefore, this would give me a buffer solution. Next, let's take a look at option number 2. So I have 10 cm³ of 0.1 mole per dm³ of HCl. So HCl is a strong acid. And 20 cm³ of 0.1 mole per dm³ of sodium ethanoate. So at first glance, it might seem like I have a strong acid and a salt containing conjugate base of ethanoic acid. So at first glance, it seems like I do not have the components required to give me my acidic buffer because I do not have my weak acid. However, don't jump to conclusions so quickly. So let's take a look. So now HCl dissociates fully because it's a strong acid. So it dissociates fully to give you H+ and Cl-. And your salt, CH3CO2Na, also dissociates fully to give you CH3COO- plus Na+. So then, is there a possibility that there could be a reaction between CH3COO- plus H+ to give you the weak acid, ethanoic acid? Okay, so there is this likelihood. Agree? So then let's see whether we have both components, the weak acid as well as the salt containing conjugate base. So to do that, I'll need to write out an equation. Okay, so over here, I can do the I's table. I stands for initial, C stands for change, and E stands for equilibrium. So I'm looking at the number of moles or the amount of that particular species at these 3 stages. So let's look at I first, initial. So what is the initial amount of ethanoic ion? So the ethanoic ion comes from sodium ethanoate. And how much of that would I have? I have 20 over 1000 times 0.1. That will give me 0.002 moles. And the H+ comes from HCl, and I have 10 over 1000 times 0.1, which is equal to 0.001 moles. At the beginning, I have no weak acid. And then over here in this reaction, my mole ratio of ethanoate to H plus is 1:1. So therefore, over here, H plus is my limiting reagent. So I will minus away 0.001 and minus away 0.001 and plus 0.001 for the product. So over here, I'll have 0.001 mole of ethanoate ion left, 0 moles of H plus left, and 0.001 mole of ethanoic acid left. So I don't really need to care about the concentration as long as I know, like, at the end, at equilibrium, I have my weak acids and my conjugate base present. As long as I have these two components present, I have my acidic buffer. Therefore, this is an acidic buffer. It would give me that. So therefore, number 2 is also correct. So take note of that. Usually, most students would say that number 2 is not a buffer, but it is. Next, let's look at number 3. So over here in number 3, I have HCl, which is a strong acid, as well as magnesium ethanoate, which is the salt-containing conjugate base of ethanoic acid. So at first glance again, this seems as though it is definitely not. Let's check it out. So my HCl, being a strong acid, dissociates to give me H plus Cl minus, and my magnesium ethanoate dissociates fully to give me Mg2 plus 2CH3 COO minus. Okay, so what can possibly happen is that my ethanoic ion can react with my H plus to give me my weak acid, ethanoic acid, like the previous example. So let me do the ice table again. So over here, what is my amount of ethanoic ion? So ethanoic ion, as per the question, will be 10 over 1000 times 0.1 times 2. Why do I times 2? Because if you look over here, I have, let me use another color. So if you look over here, I have 10 over 1000 times 0.1 mole of magnesium ethanoate. And since the mole ratio of magnesium ethanoate to ethanoic ion is 1:2, therefore the amount of ethanoic ion should be 10 over 1000 times 0.1 times 2. So that's how I got this value. And so this will give me a value of 0.002. And for the H plus ion, it would be 20 over 1000 times 0.1 equals to also 0.002 moles. And for my ethanoic acid, at the beginning, I have none. So then you realize that, oh, okay, they have the same amount, so therefore they will exactly react with each other. And they will give 0.002 mole of ethanoic acid. So at the equilibrium, you have 0 ethanoic ion, you have 0 acid, and you have 0.002 moles of ethanoic acid. So over here at equilibrium, you have your weak acid. However, you do not have your salt-containing conjugate base. Therefore, this is not a buffer. So therefore, the answer is just 1 and 2. And that is B. Okay, so thank you everyone for watching the video today and hope to see you again tomorrow. Bye-bye.